Alright, so I'm going to be doing chapter 28, problem 57, and the question is asking, a sphere of radius r has a total charge q. The volume charge density in coulombs per meters cubed within the sphere is rho equals c over r squared, where c is a constant to be determined. So part A is asking you to define c in terms of r and q, so we're going to go ahead and do that by integration using the left-hand side of Gauss's law. So we have part A. dq equals rho dv, and we're given rho, and in this case the Gaussian surface that we're using is a sphere, and the integral of the volume for the sphere is 4 pi r squared. So we'll go ahead and plug those in. So we're going to have c over r squared times 4 pi r squared times dr. Because the dr will be added later when we integrate. But so the r squareds are going to cancel. So we're going to get dq equals 4 pi c. So now we're going to integrate from 0 to r to get q. So that's going to be from 0 to big R because it's asking for the entire radius at any point. So we're going to go 4 pi c dr. And the 4 pi c is a constant, so we're going to pull that out. So it's going to be 4 pi c 0 to r of dr, which then in turn just equals r. So it's going to become 4 pi cr equals q. And to define c in terms of r and q, we just divide. So c equals q over 4 pi r. So now that we're done with A, we're going to go ahead and write this down because we're going to be using it for these next few. So c equals q for 4 pi r. And that'll come in handy for the next part. So I'm going to go ahead and erase this. Okay, so now part B is asking, find an expression for E when r, the little r, is less than big R. So in this case, let us look back and see that the enclosed integral, the electric field dotted with area equals the enclosed charged over epsilon naught. So we know that with this Gaussian surface, if we integrate once of the area, it's going to give us the volume, which is 4 pi r squared. And since it's a Gaussian surface that applies to this situation, the dot product is removed. So we're going to have E equals 4 pi r squared equals qn for epsilon naught, which in turn makes the electric field equal to q in over 4 pi epsilon naught, which we remember is 1 over 4 pi epsilon naught is k, the electric constant, times r squared. So now we're going to go ahead and use this to our advantage. So here we have q equals the integral of dq, which we also saw earlier to get this, which equals rho dv. So we're going to go ahead and plug these in for 0 to little r because it's going to be less than big R, so it's going to be enclosed up to little r. So we have from 0 to r, c over r squared times 4 pi r squared dr. The r squares cancel, and then we're going to go ahead and plug in the c value that we solved earlier. So then this is going to become q over 4 pi r times 4 pi dr from 0 to r. And as you can see, the 4 pi's cancel. So then this is just going to become, for dr, it's going to be just r. So then we're going to go ahead and bring this up right here. So then it's just going to become q r over r. And we know that epsilon naught equals qn over 4 pi, or the electric field is q, the charge enclosed, divided by 4 pi epsilon naught r squared. So we're going to go ahead and plug this in for q. So we get qr times 1 over 4 pi epsilon naught r squared, which then in turn makes the electric field, when r is less than r, equal to 1 over 4 pi epsilon naught times q over r times r hat, because this is still a vector and still needs to be solved. So this is the answer for part B. So I'm going to go ahead and erase this. So now part C is asking, does the expression have the expected value when little r equals big R? So for that, we just go ahead and plug in the large r value for the little r value that we have in here. So for part C, all this really is E equals 1 over 4 pi epsilon naught times Q over R times R hat, which then just makes it equal to 1 over 4 pi epsilon naught times Q over R, big R squared R hat. And that is your answer for C.